My name is Wilhelm Huck and I'm your host tonight. I'm super excited, we are super excited, Sam EE and me are super excited to be here live in the Gigabyte Cafe of our very own Huygens building at the Faculty of Science of Radboud University. And for those of you who have been watching us online or here in the audience, in season number 1 we discussed the origins of life, and then season 2 we discussed artificial life. And this season, we are going to do something very, very different. And so let me introduce the topic a little bit to you. As you know, chemistry is probably the most complex discipline there is. So the parameter space that you have with all the molecules and all their interactions between the molecules, creating complex systems, as in something we call life, is so enormous that despite all these bright chemists out there doing experiments for more than 100 years, we're reaching the limits of what we can do with a standard, old-fashioned chemistry lab. And that's why we decided that this year's topic should be different. It should be about chemistry and AI. And this is also a little bit inspired by a rather substantial grant we were awarded last year, like 97 million, to build a fully autonomous, self-driving robot lab, where you have high throughput experiments, automated data collection, and indeed AI to really sort of transform the way we do chemistry. That's the ambition, which really means we need to actually build a robot lab, something a little bit more sophisticated than this. We have to do all the data analysis, but above all, we need to get to grips with chemistry and AI. And that is the topic of this season. And so therefore, we needed to find some world-leading experts in the field of AI, computer science, chemistry, robotics, etc. And we have a really nice lineup for this year. And I hope you will enjoy watching all the different episodes. With that, I would like to introduce the first speaker who is kicking off this season, Dr. Tal Kachman, our very own Tal from Radboud University. He's an assistant professor since a couple of years. It is my pleasure to read on his CV that he actually started studying chemistry back in 2004 at the Technion in Israel. But then he changed to physics and mathematics, and indeed did a PhD in physics, combined at the Technion and at MIT under joint supervision with Jeremy England, familiar with some of the chemists here. After that, he was a postdoctoral fellow at IBM for a number of years before setting up his own company, Rhizome Works, in New York, where he was founder and CTO. The company is doing great, but Tal has moved on. He first worked actually at a hedge fund at AQR Capital Management in London. And I guess now he has retired and he has time to follow his academic interests, his hobbies, I guess. And he joined the AI faculty at Radboud University in 2021. And it's a great pleasure to have you here. He's heavily involved, of course, in our endeavor with the robot lab, and he will talk a little bit about his contribution, hopefully, to the field. Before Tal starts, for those of you watching online, save your questions, put them in the chat. I can see them after Tal's talk, and then there will be plenty of time for discussion. So Tal, the floor is yours.
Thank you so much, Wilhelm, for the very kind introduction. I just want to make a small correction that I was co-founder of Rhizome. I had a phenomenal partner in crime that really helped me and inspired me to do all of this. And he was actually sort of the main driver of it. And I'm super happy to kick off, I think, this wonderful series, talking about the scientific understanding that we can glance from AI. But sort of when preparing for this talk, I thought about, well, we can gain a lot of understanding from AI about how science works, but that's sort of like a very directional statement. I think a more correct way to think about it is actually sort of what is the science of learning? And more importantly, how can we learn from science? And I think reflected in what we are trying to achieve in the RoboLab, this cycle is a very natural one. And with that, let's get cracking. So I cannot really talk about this sort of like very nice cycle of learning of science and the science of learning without really acknowledging the fact that I had a phenomenal set of mentors that really taught me what science is. So I really want to acknowledge Jeremy, Jacob, Hagai, and Alexia. I think more importantly is sort of science of learning. And that is the acknowledgement that I have a truly phenomenal group of graduate students that work with me. So Leo, Shakib, Voiko, Thomas, Mauricio, and Stefan, who's unfortunately not here, shout out. You guys are phenomenal. And it makes it really an interesting experience to do science. So sort of, I was very excited to give this talk because when William told me, oh yeah, this season is about chemistry and AI, as William sort of mentioned, it's actually a lot similar to my own route in science. So I want to give you a bit of an overview about my scientific random walk, where, as William really said, I started from thinking about chemistry, about physics, about mathematics as a bachelor student. And from there, sort of, with the understanding that as technology advances, we actually have phenomenal tools to look at such systems in vitro or on the computer, I actually went and did a master's in high performance computing at the Technion. And after my master's, I was extremely lucky to do my PhD with Jeremy England on the topic of statistical mechanics. Sort of how can small microscopic systems be averaged out to sort of exhibit macroscopic phenomena. More importantly, we looked at systems out of equilibrium. So you have like this weird behavior. And this was sort of my start in chemistry, in physics, and in computer science, in the life sciences. But as physicists know, sort of when there are changes in temperature, we undergo a phase transition. So after sort of being buried in Boston for a good chunk of time in the snow, I decided to transition into AI, where, as William said, I had a phenomenal time working in IBM research, thinking about how does learning theory and machine learning relate to healthcare and the life sciences. So what can AI tell us about healthcare? And afterwards, we had Rhizome, which thinks about how can AI innovate and drive large-scale mechanical systems. So if you think about, for example, even this building, right? Look above you, this ventilation is a very, very, very complex system. It has a lot of different rotors. It's like a very hard problem and just shouts for control with AI. And following which, sort of, I took a random walk towards Wall Street, like a good physicist, and I worked in AQR Capital Management, thinking about machine learning, AI, deep learning, and how can you think about optimization, time series forecasting, how can you sort of predict natural phenomena. And sort of, I had a very long and winding road. And in general, so Pablo Ionis was here last season, and he said that he also always considers himself a nomad, because he sort of, throughout his academic career, had 7 different countries. Well, sort of scientists are nomads not just like spatially, but also conceptually. So I had sort of the pleasure or mispleasure of actually changing 7 disciplines, 8 cities. I think I lived in some airports at some point. But all of this is to say that if you're doing science from the undergraduate level to the assistant professor to the full professor, like, shout out, you are doing an amazing job. More importantly, you have a phenomenal scientific community that I saw as well, sort of like transitioning between the different disciplines that can really pick you up no matter how hard it is. So I really want to encourage you to both be sort of a scientific nomad. Try and explore as many different disciplines as you can, but also try to interact with your scientific community. We often don't sort of leave our own office doors, and I think it's super important to do so. So with that, I want to talk a bit about science, which is why we're here. More importantly, sort of, I want to talk about what's in common with everything that I mentioned, right? So I told you, like, all right, I worked a bit on like physics, on mathematics, on computer science, on chemistry, and statistical mechanics. Like, there is this whole horde of different disciplines, and they have one very beautiful thing in common, in that they are all sort of facets of something called a complex system. Right? In different manifestations, in different properties, and in different settings. Sort of, so what's a complex system? Well, complex systems are super intriguing. Complex systems are systems that are composed of many components that interact, right? But more importantly, this interaction or the collective behavior of them gives you a nonlinear phenomenon and something that is different than the sum of the parts. So I take two things, I put them together, and I get something completely new. And we often think about complex systems, sort of we imagine like these huge systems with millions of particles, millions of building blocks. It can actually be much simpler, right? So I think a striking example is chemistry. You take two hydrogen atoms, you smash them with an oxygen atom, and you get water, something that's sort of completely different property than its constitute building blocks. Something else that is near and dear to my heart, financial markets are complex systems, right? You have different people interacting through different venues and different exchanges. Every time you have something new, you have a whole different system, which is extremely hard to model. Sort of coming from the Dunder's Institute way down the road, it would be amiss of me not to talk about, for example, the brain. You take one synapse, you add another synapse, you add another synapse. Slowly, every time you add, you have a whole new system. And sort of you have this emergence of the phenomena of thinking, of conceptualizing, of understanding. And of course, in the interface between chemistry and AI, neural networks. So our lives are now basically dominated by this sort of computer science algorithm called neural networks that has building blocks which are called neurons. And the more neurons you add to these kind of models, the more you can solve or understand or express harder and harder problems. And we don't know yet, when we tack on a new layer, more neurons, what happens? How does the model change? Right? So you have this wonderful theme of really systems that you add different components to them, and you get something completely new. And I think, sort of thinking about all of these examples together, gives you this wonderful mechanism of taking insights from the natural sciences and thinking about this kind of like artificial complex systems and what kind of insights you can get from the artificial complex systems into this natural science disciplines. So to be more specific, because we are on the topic of chemistry and AI, I want to give you sort of two sides of a very wonderful coin. And the first one is, how can chemistry help us with AI? And for that, I want to talk a bit about AI. So how do we usually look at AI in the AI department? We usually think about some sort of set of empirical observations, data, which we often call features and labels. So feature is the empirical observation. Labels is what describes it. And I'm going to give a few equations, not too much. And we usually think about them as this set of observations. And we say, well, you know what? I got like a very small subset of it. I have no idea how it generalizes to something bigger. So in fact, we make some assumptions and we say, well, if this is the data, then the data has some sort of distribution, because that sort of gives us a way to conceptualize or learn how to generalize, how to basically classify or understand unseen things. So by looking at this set of empirical observations, we want to try and learn what is some sort of underlying statistical universal property, and from that leverage to unseen cases. Very similar to sort of like how you do experiments in the lab, in chemistry or in physics. You collect your empirical observations, and then you try and build a model to generalize and understand this phenomenon. Sort of put it more concretely, the learning problem is understanding this distribution. And there are two types of learning. One is called discriminative learning, where I try to sort of, you give me the observations and I tell you the label. You give me a picture of a cat and I tell you it's a cat, etc. I think what's more striking, and it really has exploded in all the possible venues, is something called generative learning. That basically I try, from the understanding of the underlying distribution, to generate new empirical observations. And so this is called the learning problem, and these are two facets of it. And what I'm going to focus on now is actually just generative learning, because what I'm going to show you is that there is beautiful physical and chemical insight into this problem. So a bit more technical. what's so hard about this problem is that if you think about it, usually you characterize this data in some sort of space. It's called a feature space. So you can, for example, think about this axis as distance of eyes to the nose, and this axis sort of like beards or something like that. And the data is sort of, depending on its characteristic, is distributed usually in a very weird way. And if we want to find the underlying distribution or the characteristics of these points to generalize, it turns out that it's very hard. It actually looks something like this. And this is a bit technical, but the point is that fitting these things are very hard. And this is a toy example. Our usual data sort of lives in extremely high dimensional space. So how can we circumvent this problem? This is where our semblance of physics starts to come in the following way. So these data distributions are skewed, and in high dimension, they are very hard to fit. So how does this relate to physics, or how can physics help us with this? Well, we can think about a noisy landscape, and this is sort of like a very nice trick that people do, is that, you know what, I'm gonna take my data, so for example, this is our puppy Maggie, and I'm gonna start adding noise to it. And in a sense, when you add noise, if you think about it, you smear the characteristics, right? So if I thought about one axis as like distance of eyes to the nose, you start to add more and more noise, and you smear it away. So it's a bit coarse. This actually makes it much easier to fit, right? But in chemistry, in physics, and in life sciences, we actually have a very natural way to think about this, that instead of honestly just adding noise and then choosing what's the best parameter, we can do a dynamical process. So I can take this picture, add some noise to it, add some noise to it, and continue this sort of like dynamical process. And in a sense, this is called a stochastic process because this is random noise. And in a sense, this is called diffusion. So this is a diffusion process. So if anyone has ever sort of like put ink in water and saw it expand, it's not that different than this one. The way it's represented is, but it's the same underlying physical phenomena. And in a sense, if we recognize this data augmentation as a form of physical process of diffusion, well, maybe we can actually leverage this. And this is where the insight from physics or chemistry starts to come in, that we can actually reverse this. We can ask ourselves, all right, if I start from the noise, is there any way to sort of reconstruct the image? And it turns out that nature gives us a phenomenal example of it. So we can take our images and sort of noise them. But if we think about the physical system of diffusion, we can put ink droplets in it. And here you see this sort of like smearing process of slowly smearing it and letting it diffuse. And what's wonderful is that under certain conditions, you can actually reverse this. I think this is one of the more striking experiments in physics. How many people have seen this? So you can actually reconstruct completely from the beginning. And in a sense, if nature can do this, maybe we can do this artificially. So we can have this thing of first taking our data, sort of diffusing it, noising it, until you get something that you can work with. And we can leverage this for generative learning or for generating data by actually reversing this process. So one technical slide, and I'm sorry for that. In a sense, if the data has some sort of distribution, you don't really need to understand the equations. You can do something called a forward diffusion. So you incrementally add the noise until you reach, after certain steps, number of steps of making this noisy, something called the Gaussian distribution, which is very well known. Physicists love it. This is our pet peeve. Everything we can describe as a Gaussian, I'll take. But what's more important is that for these kind of diffusion processes, physical processes, we can actually write the reverse. And we can leverage something called the neural network to learn how to reverse this. And why is this so important? Because in a sense, once we have an AI algorithm or a neural network that can reverse this, and it's fully trained, we can just sample things, points from this Gaussian distribution, and run it backwards to generate new images. And it turns out that using these kind of like physical insights of diffusion processes to generate images works remarkably well. So what you see here are generated images of churches. None of this is real. All of this is 100% generated with this kind of diffusion processes or learning of diffusion processes. And if anyone ever heard like it exploding all over the news of stable diffusion, mid-journey, this is actually the underlying engine underneath. It's phenomenal mathematical physics and chemistry. And I highly encourage, this is Alexia's paper, to read about it. We published it in Gotta Go Fast with generating data with score-based models. But sort of, I gave you two sides of the coin. This was chemistry or physics for AI. I want to switch and say, how can AI help us with chemistry? Well, it turns out that chemistry is phenomenal, especially in the real world. Is that if you look at most of your objects, for example, this frying pan, and you sort of like zoom in, it has a very nice structure to it. This is Teflon, right? And you can represent it as images, right? In the same way I can take like salt, I can zoom in, and this also has sort of very nice pictorial picture properties, right? And in a sense, in the same way that we learn to generate cats, dogs, like whatever you want to put into your mid-journey, we can actually take a horde of chemical structures and use that as input to try and learn how to generate, instead of new dogs and cats images, new materials. And it's even more nicer than that, because when we thought about this kind of processes, we fictitiously added white noise. So this epsilon is something called a white noise. It's noise, it's random variables drawn from a Gaussian. But nature gives us sort of its own intrinsic sources of noise, and it's called temperature. So what we actually do in my group is we take these kind of crystal structures and we run its dynamics, right? So we generate our own sort of like noisy data by running something called molecular dynamic simulations to try and build sort of a self-contained or empirical data set by itself. This is sort of like very nice because data, real data, is very, very, very hard to gain. It's also very, very expensive. And here, in a sense, by using intrinsic chemical mechanism, you can try and sort of leverage and build more data. And now you can start to use AI to actually help you do new chemistry and new physics, right? And you do some very nice things. So these are 3D printed objects in Yoav Lahini's lab in Tel Aviv University, where we took this sort of like horde of deformed or different moved data, and we actually learned using neural networks to generate these kind of things. And this is some example that gained from it. And these things are very unique because this is called a mechanical metamaterial, because you can think, all right, you're just learning images and to generate images. Like, it's very hard to learn physical properties. But it turns out there is a whole horde of materials called mechanical metamaterials that all of their functionality is actually encoded in their geometry. So there is this beautiful example where usually you take a material and you squeeze it in one way, it will expand in another way. Here, learning this kind of like lattice structures that are a bit deformed, you get something very nice that you see that it actually collapses inwards. Right? So really I want to encourage you to think beyond just generating images of cats and things. And you see that you can get wonderful insight into chemistry from these kind of like generative models. And with that, I want to give you one more example that I think is very nice. So part 2, act 2, of how AI can help us with chemistry. And it's something a bit more of a mathematical nature. So I apologize for that. Well, I think it's very nice. So I showed you this kind of very nice crystal structure, right? And this is called a hexagonal lattice. And what's very nice about it is that sort of like nature and symmetry gives us stability. In a sense, if I put some sort of, for example, dot here, like an atom, because of the symmetry, all of the forces working one on top of another cancels out. And this is the property of the symmetric. But it's sort of like, this is a very nice example that it works on a flat space. And I show you here, sort of, unfortunately, nature is not flat, right? Like, Life is complex. It's in 3D. It has like different geometries. So in a sense, what we should really think about is how to take these sort of structures and actually embed them on a sphere. So think about taking this sort of hexagonal lattice and putting it on a sphere. But embedding is super hard, right? So I encourage everyone at home to do this. So try and take like this kind of hexagonal structure and put it on a sphere. Actually try to compose it. I'm not sure the camera can see it. You will see that you will never be able to reconcile it. So you can't really, it's called embed, this thing perfectly. You will always have singularity. So you stretch it. This is called geometrical frustration. That you take something that you want to embed it into a different dimensionality or different manifold or different geometry, and you can't do it because something gives. Here the example is that the lattice will deform. And you all know sort of like a very nice example of a very particular case of 60 points, and that's a soccer ball. So if you ever ask yourself, why does a soccer ball have hexagons all over, but pentagons in the polars? Because that's the only way that you can actually fully in a stable way embed a hexagonal lattice onto a sphere. And you can sort of like ask yourself, all right, why is he talking about this mathematical property of embedding and things? Well, you actually see a form of embedding every day. It just looks like this, right? So in fact, when you do these sort of searches in Google and you have this autocomplete, for example, deep learning word embedding, this is how the autocomplete works. What it does is it takes an atlas of words, it learns some sort of embedding or geometrical relationship in this data space that we talked about, and it looks by similarity what it needs to complete. So it turns out that neural networks are phenomenal and embedding for them is very easy. So we can take this kind of embedding methods that people use in NLP, in language, in all other kind of like geometrical learning, and use it to do deep learning for frustrated system. So how can you take this sort of almost biological or chemical systems and embed them in a stable way? And what you see here is another molecular dynamic simulation of finding such an embedding for a generic case. This is not 60, this is a bit more than that. And it's a very stable one. So you see the hexagonal facets here sort of like shift and move. So it turns out that you can actually leverage all the wonderful world of AI and what AI knows about embedding and learning geometries, actually learn physical systems. And with that, I want to sort of like start wrapping up a bit. So I think there is a lot to go here. As I've shown you, there are a lot of examples of how you can really take sort of the science of learning. What does AI give you? And play with it and get insight from it to the learning of science. How can you actually learn physical systems? So from using physics and chemistry for AI to go into actually utilizing AI to understand physics and chemistry, and round and round. And I really do think that we're at the golden age of this kind of scientific discovery where we have hordes of data, we have all the amounts of compute that we want, but we also have all of the problems open. There is so much to do, which is why I'm so grateful to be involved in what really closes this loop nicely, and that's our very own RoboLab, right? With the growth fund that Wilhelm acquired, to really create a fully autonomous self-driving laboratory, AI-driven, and what sort of like insights can you get from the chemistry there to maybe understand AI better. And with that, I want to acknowledge just one very, very, very important source of funding. So I'm very lucky to be funded by Lineage Logistics, really a company that is a net positive to the world. They do large-scale logistical chains. So the fact that, supermarkets weren't empty in COVID, shout out to these guys. They do logistics of food and medicine, right? And I'm truly honored to work with them. And sort of acknowledging the real heroes of this one last time, which is my group, I want to give you these two sort of takeaway messages. One, really think about how can you take all the different tools from the science, from chemistry, from physics, from AI, and create new things. But honestly, just enjoy doing science. And with that, I'm more than happy to take questions.
It was a wonderful introduction. To kick off the season, I think chemistry inspiring AI and AI sort of being used for chemistry. There were quite a lot of concepts that I still need to wrap my head around or embed my head in, I think. But I'm sure we can discuss them now. I invite everyone to ask questions. There will be some questions coming in there. We'll be sitting on the couch, I guess, and we'll have another half an hour to chat. So any question in the audience? Otherwise, I'm happy to start by going back to this diffusion experiment, which you can do yourself if you actually make chocolate chip cookies. And you sprinkle in the chocolate chips and you stir in one direction. And if you then stir in the opposite direction, you will be amazed that this really works. So as a chemist, though, I would always say that works because there is no diffusion, because there's a viscous medium and the chocolate chips are really rather large, so diffusion is so slow that by just moving them around, you can move them back because they didn't diffuse. Yeah. So I was actually rather puzzled by this idea that you use diffusion to then work your way back to hundreds of pictures of churches that don't exist, because I thought exactly that would happen, because from this Gaussian distribution, you couldn't possibly know what the original picture was, right?
So that's where you start to really leverage AI, because even in that example, for example, the viscous fluid or the chocolate chip cookie, you always have some noise around it, right? And it's that noise that actually lets you generalize. So it's a combination of the fact that it is reversible, but not fully, that lets you generalize, right? So in a sense, it is a diffusion, but it's on a very, 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 very short scale. And it's not trivial. So if I would just allow nature by itself to really reverse a fully diffusive process, that won't go. But luckily, we have AI that we can actually take small increments forward, small increments backwards, and learn how to reverse this trajectory. So you learn this. That's the learnable part.
So that does mean when you start with the picture of a church, you first diffuse it, and then you go back. Otherwise, you won't end up with a church, right?
Exactly. You need to learn the relationship of how to go from one space of pictures to the Gaussian, and then from the Gaussian, you need to go back. So you need really the full cycle of it. You can't just do it one way.
I think that's very exciting. Questions? Yes.
Gray. At some point it's fully gray, and at some point you can fully reconstruct it. How do you know where to aim? When is it enough complexity in
So there are a lot of terms in that question. It's not as much about complexity. So there is this wonderful thing of diffusing it forward. You can construct a diffusion process. You actually know which Gaussian you hit and what you can fit it even. So there is a question. The question is, well, how much data do I need to diffuse to actually fit this Gaussian well? How much data you need? That's like the loaded gun or the elephant in the room in AI. For regular machine learning, there are some sort of methodological things to actually estimate sample complexity, these kind of things. Well, for these kind of methods, usually you have big enough data sets for natural data, like cats, dogs, cars, stuff like that. Honestly, when we think about the physical sciences, about, for example, this chemical in this chemistry experiments, that's where it gets tricky. And that's a big part of why we're sort of like trying to bootstrap or generate our own data. Because you really do need large amounts of data to train this. I can say that all these diffusion models, and there is a whole family of these, are a bit easier to train or to control than sort of like their predecessor, which is called a GAN, a General Adversarial Network. They are more well-tempered in training, but you still need copious, like not copious amounts of data, but you need a good chunk. For example, if people if people notice things like MNIST or like the regular data sets, those are enough actually. Like 10,000 observations, like 12,000 observations is a lot. Where Wilhelm is sitting next to me and say like 12,000 empirical observations, well, that's like.
With a robot lab, that's kind of okay, I guess. And a lot of students, I don't have to do it myself, so sounds doable.
Yeah.
but not much more than that.
Yeah, it's already pushing the boundaries, and I think this is also one thing why we want to leverage these sort of relationships, because there are hurdles from going from like this synthetic or sort of perception data to really trying to use AI for the life sciences.
Other questions?
Thank you. Do you hear me?
No, it's not
No.
on.
Well,
Otherwise,
I
shout.
can. That you consider your reality. So there is no noise there, right? And then
Well-
you introduce noise until you lose and you get your Gaussian distribution.
Mm-hmm.
So you learn how to reverse from the Gaussian distribution to the absence of noise, let's say. But what if you start from data that contains noise that you don't understand? Do you think AI could be used to push that and remove the noise from that starting data?
So there are two caveats to give on this, is that all data has a form of noise in it. Nothing is perfect, and no free lunch. You will always get it like that. You touched upon a very good point, and that's a big reason why we sort of see 10,000 image generation platforms and approaches. For example, generating healthcare data, or generating something called tabular data, or even time series. It's much harder, and it's exactly because of that you have a unique combination of data sort of starvation or scarcity, but also a lot of intrinsic causal noise into it that makes it hard. And that's actually an extremely active field now in AI, basically using these kind of things. And it's very similar to how we try to generate new chemical structures or compositions to try and generate different type of, it's called the modality of data, right? So this is a very personal opinion. I really do think that yes, AI can do this sometime down the line. And you know what? Even if not, I think even sort of like more insightful is that you will start to understand more and more things, both from the success and the failures of these approaches, right? If you start to synthesize, for example, healthcare data, and you see like, oh, I only get this kind of patient, then you know, well, I have some sort of systematic bias in how I generate it, and you can actually sort of start to trace back, almost like a detective, where it comes from, going back to the real insights that you can get from AI into this kind of applications.
Maybe I had a follow-up question also from the earlier questions on data generation. So you now go from a picture of a church and you diffuse it and you go back and forth and you generate thousands of churches. If I start with a molecule and I sort of now use my diffusive process to generate thousands of molecules that don't actually exist, as you said, with the church. The problem is if I have a molecule on my computer that I can't actually make, then what is the point of having a picture of that molecule? How do we go from there to something where I can distill still some properties of these non-existing molecules or proteins or something else, right? Yeah. That I can still learn from that collection of sort of non-existing sort of entities that I can still use then to make something that I can actually make later on.
So it's a good point, and honestly, there is also a long process of discarding things, because you really do just learn by thinking about it as images, but images can't really, for example, capture solubility, can't really capture electronic structure. But we do know, for example, from phenomenal experiments like AlphaFold 2, that you can, by infusing physical knowledge into the generation process somehow, actually generate things that have physical or chemical characteristics. And that's
so does that mean that in your diffusion process you can also add a step where there is some kind of something that captures the physical property or the molecular
For example,
structure?
you can think about crafting the potential for the stochastic diffusion process, right?
Yeah.
You can always add underlying energy landscape
Yeah.
or potential or force, right? And I think that honestly, this is the future, sort of synthesizing these two approaches of taking the AI and infusing it with chemical knowledge.
Other questions. I'm looking online. Amy has a question, and she says, how much does the quality of input data matter? How can we avoid bias in these training sets? I think that's a little bit what Oscar was alluding to in terms of noise, but I guess what Amy is saying, that there's not only noise in your data, but
There's also bias,
well, especially in the chemistry data, all the chemists have only published the experiments that worked. Nothing else, and probably everything was perfect, so all the side products they didn't analyze. So there's a huge amount of bias in your data in the sense that it's the
100%.
flavor of data that you will be training on.
100%, and sort of a bit of a self-advertising. In my group, we work a lot on sort of AI for the life sciences, but we also work a lot on the foundations of AI and machine learning and understanding what's going on there. And honestly, uncertainty quantification, or sort of like biases and confounders inside models, are a big topic. So this is, again, everyone is hitting like these open questions. There is always systematic biases just from the fact that you have a finite amount of data and it's sampled. And there are methodologies to de-bias some stuff. And there is a phenomenal paper that I highly recommend everyone reading. It's called Man is to Computer as Woman is to Homemaker, how to de-bias word biasing. So you have these huge language models, right, that are trained on humongous corpuses of data. For example, 100 years of these have like gender bias inside of them and all these things. So there are two types of biases you can think about. One that really stems from the fact that you never have full observability into like the whole data distribution, but also one from how your neural network or AI architecture is composed. So you really need to start to think how to take the tools that we have now to de-bias. For example, one thing that people do is actually called dropout uncertainty, where you take the neural networks, they start to either omit data points or things in the neural network itself. And by looking at the omission, the results that you get, start to quantify the uncertainties in the model and then correct for them. So it's a long process. And honestly, all of these questions are phenomenal because sort of in the context of deep learning and images and stuff like that, there are a lot of results, but it's sort of like still going. With respect to thinking about AI in the natural sciences, it really is sort of like brand new territory.
And the robot lab, of course, is not biased at all, right? That will just collect data. Will not be unhappy if something didn't work. It will just report. So that's a good thing. Another question I had was actually going back to your embedding, where you showed a little bit these sort of different sort of, well, a football sort of lattice. Is that something that you could start to apply to make new cages? So, for example, viruses have all these capsids. Is that something that you actively will be pursuing, or you say other people are already working in that space?
Other people are already working on it, and we're slowly starting to streamlining into them by sort of bringing our AI approaches into them. For example, you have Lahini in Tel Aviv University that did some of the other work and is a very long-time collaborator, actually actively works in this. But definitely sort of the material design or the mechanical material design is something that we're gonna
so coming back to that, so obviously in terms of the, say, a virus capsid, it is mostly about fitting the space, right? So to make something that is geometrically such that it will somehow sort of form a symmetrical structure. If you think about more liposomes or sort of cell membranes, it's much more about having the optimal properties in terms of fluidity of the layer, permeability, stability, bending rigidity, and all these kind of things. Is that something that you think would be reachable, or is that still very far away? How do we go about sort of
I think we're on the way to it, to sort of like, in a sense, have this cycle between, because what we're interested in a lot actually is this question of like self-assembly and optimal self-assembly. So I think we're on the way there by this sort of cycle of looking at just the molecular dynamic or the chemical simulation, sort of at some stage stopping, running this kind of like deep learning embeddings and understanding of the geometries and how to optimize, and then restarting the molecular dynamics or the chemical systems, very similar to how you go from an optimization, a cold start problem, to a warm start problem, that you utilize your past experience. So you can do this sort of like intermediately and go there. This is 100% open research that we're still pursuing in my lab.
Very exciting. I think that's something that in the robot lab will definitely be a topic in the future.
Well,
So
it's
very nice.
It's definitely.
Questions? Looking around. Emma. Sorry, I missed you.
My question is a bit more sort of zooming out, I guess, and or maybe there are two questions actually. The first is, what do you think is the biggest challenge in this approach to really make it a success? And the second is, well, assuming that it will be a success, will eventually the sort of the classical empirical determinism-based science become obsolete?
So it's a good question. So just to address your first one, I think the biggest hurdle is really going back to William's example of synthesizing molecules. Be very afraid of garbage in, garbage out, because AI can give you like whatever you want. And actually, in a sense, you can call this overfitting a form, or more importantly, what sort of we coined in my group, like cultural overfitting, is the fact that everyone is doing these things on the same data sets and the same things. You sort of culturally craft something that doesn't really generalize well. And I think one of the biggest hurdles is in infusing the domain knowledge, the human knowledge, or the scientific knowledge to avoid this kind of garbage in, garbage out results, right? You want to infuse the AI with your own sort of domain expertise to try and navigate it to the right area, right? It really is, in a sense, almost a human in the loop learning paradigm. And I'm sorry, what was the second question? No. I really don't think that we become obsolete in the same way that sort of like everyone says, like, oh, all of these models like will replace all the artists ever. Like, we don't need any more illustrators and stuff like that to generate. I really don't think it. If you look at how these things work, you still have a lot of something called prompt engineering, like understanding how to give it the right input to get what you are. I don't think that scientists will be obsolete. I think this will be more of like a regular tool, in the same way that sort of computers went from punch card to basically replacing laboratories as a tool for us to rapid prototype. These kind of things will become a tool for us to explore on faster scale, on larger scales, on more complex systems, this kind of phenomenon. Sorry?
We will have to select which Gaussians to combine to get to
Well,
an optimal solution.
Well, for example, this actually happens quite a lot now in chemistry, in something called like DFT. No one actually does like full electronic structure. You go to like a software piece, it tells you pick like which Gaussians, which basis functions do you want it to. You press click and like the optimization problem solves it for you. So it's not really new. Like, we had this evolution of something that sort of like, you know, was revolutionary to a phenomenal tool quite a lot in our scientific history.
I think we should also look at it from the positive side. So I think I also worry a little bit when Tal only talks about his generative sort of AI, and you diffuse outward and backwards, and you generate all these pictures, and then, well, you have all you need. There was not a single word where he needed experiments. So as an experimentalist, I started to worry a little bit there as well. But then on the other hand, I think it means also that we can free ourselves from the boring problems that we have been working on, right? Because you could also say all the easy things have been done by now, and we are sort of still doing some chemical reactions that we know we kind of can do, and we have to optimize them, and it's very hard and goes very slow. So you could also say, well, we can start thinking about addressing problems in a different way. And the two things that I wanted to mention there is, for example, we are now pretty good at making an oscillating system. A chemical reaction network that has a positive and a negative feedback loop, and it oscillates. And we're good, and we're happy, and we clap, and then we think, okay, it's just an oscillator. It cannot even be used as a clock because I cannot even control its frequency. It is what it is. And so when Bob, who's sitting next to you, started his PhD, he was already using genetic algorithms to sort of predict which kind of networks would actually give you a oscillator with a certain frequency or with a certain amplitude, maximum frequency, maximum amplitude. And it turns out the networks that the computer then generates are very, very complex. They have 7 different feedback loops or 13 feedback loops, and very difficult if you look at it. It doesn't look where there's any reason why this would oscillate. And what it means is that we have maybe design rules for making certain complex systems, like an oscillator, but there's no design rule out there that tells you how to make an oscillator with a certain frequency. It simply doesn't exist. And so if you then say, well, but I still want to pursue this experimentally or theoretically, there's nothing where you can start, right? And there I can see, now you have a way out. Now you have a tool maybe that allows you to generate maybe thousands of oscillators that all could oscillate with a certain frequency. And maybe at some point you start to see the light. Maybe you see patterns. Maybe you see design rules that are much more complex than you could imagine now, but then you discover them. So I think that is one direction that I think is something that sounds simple, but it's something that we can start working on. Tal didn't talk about dynamic systems, but I'm sure that is
that was
another
other
complexity. Another thing is when I'm talking to a well-known beer brewer in the Netherlands, and they are interested in the robot lab and AI, and you think, well, why would you need AI to brew beer? But they say, for example, in the short run, you want to make, for example, alcohol-free beer that tastes exactly the same as the normal beer. But alcohol itself has a certain taste and gives you a sensation in your mouth. So you think, okay, I can replace that with something else and I'm finished. But then it turns out that the taste of beer is something like 100 compounds that are all volatile and that go into your nose and then create some smell. But the problem is if you take alcohol out, the vapor pressure of each of these compounds changes in a nonlinear fashion. So it means my profile of sort of odor, or fragrances, or anything you want to do depends on the matrix that it comes from. And that means we cannot really shape the the odor or the taste of beer because we don't really know this relationship between all these different compounds and with or without alcohol. In the long run, they wouldn't actually like to brew beer. They would like to formulate beer. You just want to say, okay, I want to have a beer that tastes like this and has a little bit of that. And suppose we can define that taste, that cost function. Then you just use your algorithm to do inverse design and actually brew that beer or formulate that beer from its components in one go. So I think if you think about what we could do, if we have really a self-driving lab supported by AI, we should really move away from the problems that we're working on. We should sort of simply move into much more complex problems. So we really need you. Do not leave science. So I'm sure there's things that we can do.
Also, just to give a small caveat, so we talked about neural networks and their biases, but carbon-based neural networks also have their biases, which is why I talked a lot about generative AI. But more importantly, a lot of what we're doing here is sort of like bootstrapping ourselves with generated data that already has some sort of assumptions. You do a molecular dynamics simulation, you have to assume what is the potential, how do I put in the temperature, am I using the right unit cell? This is also like placeholders for real data. And you really should strive for real data in all of these algorithms. This is what gives you friction with reality.
Question all the way in the back.
Good night. How can the system help undeveloped countries and make the world a better place?
Sorry?
How can the system help undeveloped countries and make the world a better place?
Well, I mean, sort of having this kind of scientific understanding of how to do things better, more efficient, how to automate them, how to do them faster, definitely reduces, for example, costs. Think about this today. If you want to do like a lot of these chemical experiments, honestly, the amount of time and manpower that goes into it is quite humongous, right? If you can do this high throughput experiment somehow more efficiently and reduce costs, for example, of, well, beer is one example, but think about, I don't know, like pharma, think about drugs, think about medicine. It really is a striking way to sort of give them more accessibility, right? Even in the simplest case of some of the stuff with just pure AI, not AI for chemistry, that, for example, lineage logistics do, right? That they are the people who sort of kept you fed during COVID. They utilize a lot of AI, that they had constraints to do these things. And this is also something that makes supply chains accessible for different types of country, different price places. So it really is a facilitator of.
Maybe I can add a little bit to that. Is also, if you look at it, thousands of products, tens of thousands of products around us are based on building blocks that are derived from fossil fuels. So, I mean, if you look at any polymer plastic around you, in the end, you needed oil to produce the building blocks. That the carbon comes from oil, essentially. So if you want to replace those, then you can, of course, start with sort of a long journey to sort of study how you make polymers and plastics from natural resources. But it's extremely difficult, right? Because you have all the materials around you that have been optimized for decades to have a very, very well-defined function. So if you replace that material, it should have exactly the same function. Otherwise, your plane can't fly. Lots of other things don't function anymore. So how do you replace those materials with materials that are based on natural resources? And that is something that if we don't use AI and high-throughput experiments, will take us far too long to reach that point. So we need something that accelerates innovation in such a way that we can replace a lot of those products. Well, I think about fluorinated compounds that are no longer allowed. You have to replace them by something that has the same function, right? But no fluorine. That's not easy. So we will not be able to do that by just searching for a one-to-one alternative. We need a new formulation, new mixtures. And that is something where we need new tools to do that. And so that's where I hope the robot lab will make a big, big difference.
Other questions?
Not a
There's also
question.
one in the back, I think.
And there's one in the back. And two microphones.
Okay, so I think the event description mentioned that your research also includes the quantum machine learning. And I was just wondering if it has some applications already in science or maybe possibly in the future. What's the state of the art?
Yeah, so first of all, when you say quantum machine learning, there's actually two ways to skin this question. You can ask yourself, all right, am I taking classical machine learning algorithms and trying to put them on a quantum computer? Or actually, am I trying to take machine learning and deep learning and design or get a better quantum computer? Because if you think about it, in quantum computing, you have this kind of gate that you do from electrons or photonics, and like it's to the point where the physical distance actually matters, right? So it's actually a great optimization problem to try and see, all right, how do I reduce something called decoherence and things like that. The majority of our work actually goes on the first part of taking regular machine learning algorithms and understanding how to put them on a quantum computer. Because if you think about it, regular computing is irreversible. But quantum computing, by how the circuits are built, are actually time reversible, right? Like it's unitary operations. So how can you do any kind of inference on something that's like fully reversible, right? There is a lot of big challenges on it. So we are looking at, for example, how to take regular learning algorithms like SVM, like even honestly, just backpropagation, like the workhorse behind deep learning, and understanding how to translate it into a quantum computer because of how dynamics look like in quantum computers and stuff like that. But it's definitely something that we are pursuing, sort of taking the classical understanding of how dynamical algorithms work. These neural networks are dynamical algorithms, and quantizing them.
We're reaching 9 o'clock, but there's time for a final question.
Oh, sorry, that was a bit loud. In the context of kind of the beer talk you had before, now obviously ChatGPT is a whole big deal right now. I know.
I was wondering
yeah,
if you're
it was
going to bust it
bound. But in particular, I stumbled across a very interesting approach that someone took to it, where they asked it to make crochet patterns. And it turned out with some absolutely hilarious and arguably terrifying creations that I really recommend people look up. There's a good article up about it. But it really, now obviously ChatGPT was made for crochet patterns. But it really shows this kind of lack of understanding that the program has to, okay, the underlying principles of crochet and how do you make a narwhal not have a tiny little, you know, horn or a giant one and eyes to fit and the head and etc. How do you infuse a program with understanding?
Yeah, so that's a good question. And first of all, like usually when people ask me about ChatGPT, I invoke my Fifth Amendment right because it's such a hilarious topic. But let's steer away. And first of all, I want to give the caveat that ChatGPT is still completely closed in the sense we have no idea what's going on under the hood. OpenAI did not release any code, what kind of data it was like trained on. We have no idea what's going on in that black box. But I'll take a step back, and if you remember, like 4 or 5 years ago, all these generative models, you used to get like pictures with like thousands of eyes and these psychedelic things. It's not there, but it's gonna get there. And honestly, me and Wilhelm have a joint student, Stefan, who's working on similar tools. So what sits, or what people sort of think sits under ChatGPT is something called large language models, like GPT-3. And underneath it, what sits is this phenomenal technology called transformers, which is a way that neural networks learn how to sort of understand the importance of past samples. And we are actively working on taking these kind of tools for chemistry, for understanding chemistry. But this goes back to sort of like the same theme that you can't just let these things run wild without any guiding hand of a scientist infusing it some sort of ground scientific truth.
Unfortunately, that's all we have time for tonight. Let's thank Tal again for kicking off this season in style. Thank you. Thanks a lot. Thank you all for those of you watching online. Make sure you register and sort of subscribe because we're almost at 1,000 subscribers, so we have to make sure that we hit that tonight. And I hope to see you all back next month, 14th of March, 8 p.m. We have Robert Police of the University of Groningen talking to us also live on stage. For those of you who are online, you'll have to sort of switch on the kettle or do something else. We have time for drinks, so join us all for drinks and chats and sort of have an enjoyable evening.
Thank you so much, everyone.